Okay, do not worry about the sign. Okay, it is based upon the moment vector. That's why you don't see any textbook teaching you moment vectors on this. I deliberately want to teach you because now it can get really, really confusing. Yes. What does student get confused? Student get confused on the sign, and student get confused what is IYY and IZZ and what is Y and Z. Okay. You all should not be confused anymore because of the technique I've taught you. Okay. So now, if you want to find now, I'm going to call this, okay, this over here to be our theta. Okay. And we know that my is equal to m sine theta, and mz is equal to m cos theta. Okay. Now I'm going to label 4 points. Okay, I'm going to label 4 points. I'm going to show you what does it mean to be what? Unsymmetrical. Okay, I'm going to show you what does it mean to be unsymmetrical. Okay, so we're going to label this point as alpha, beta, okay, I, and J. Okay, so we're going to write down here. Okay, so we're going to write stress X alpha, stress X beta, stress X I, and stress X J. Okay, then we are going to look at the moment Y. Okay, so moment Y, I use blue color. Okay, so I'm going to my. Okay, my. So for my, right? If you look at my, right, alpha is in tensile. Yes or no? So I want you to focus on moment Y. Okay, so alpha is in tensile. Okay, so this is positive. Beta, due to moment Y, is compression, negative. I is in tensile, right? J is in compression. Okay. Then we next look at moment in the Z, right? So moment in the Z, right? So you look at now. I want you to focus on moment in the Z. This one. Okay. So when we focus on that, so in alpha, you have compression. Beta, moment Z, also compression, right? And stress X in I due to moment Z is in tension. J is in the tension. Okay. So what you realize over here, right? If you look at stress X alpha and stress X beta, right? So we realize that stress X alpha is not equal to stress X beta, right? It will not be the same at all. Likewise, if you look at stress Xi, will not be equal to stress Xj, right? So, and also for this case, I need to declare moment about Y is not equal to moment about Z. Okay, I want to declare that to all of you. So what you see now, this is what we call, okay, unsymmetrical loading. Remember, symmetrical or unsymmetrical loading is what? It's a normal stress function. Okay, now let me recall to you what do we mean by symmetrical. So if you look at last week, okay, this is last week note. Right, last week note. Okay, so if we look at last week note, symmetrical means alpha is equal to beta, I is equal to J. Alpha is equal to beta, right? We show that alpha is equal to beta, right? For this case now, right? Not For this case now, alpha is not equal to beta. Why? Because you can see this, right? This is plus, this is minus, these are both minus. They will never be the same. Okay? So this is what we call, okay? So what you see over there, the formula that we have applied now is known as centric, okay, unsymmetrical, loading. So if you want the true form of the formula, if you look at any formula books, okay, is equal to my over Iyy multiplied by z minus by mz over Izz multiplied by y. Now, if some of you were to ask me, Eugene, why mz is minus? Because the z arrow down here, right, or the z-axis over here is pointing towards negative. Because we have the conceptual that positive is towards the right, positive is going up. Okay, so you see z down here is pointing negative, that's why it's negative. Now, if now the whole thing is under eccentric, unsymmetrical, loading, how will the equation look like? Okay, so it's very simple. It's equal to px over a, okay, plus by my over Iyy multiplied by z minus by mz over Izz multiplied by. So this is due to axial loading. Nothing changed, okay? The concept is still the same, and this is due to bending moment. Okay, so the key feature over here is again the moment vector. Compression, tensile. That's it. Okay. One thing apply for everything. That's the best thing. Okay. Now let's look at one more example. Okay. We look at one more example. Then I'm going to show you how to derive the position of the neutral axis. Okay. Let's look at example number 3. It's not any more difficult. Okay. It's just you have another vector to apply. Yeah. You just have another vector to apply. So let's look at a. Oh, I think my bad. When I paste this, I don't think you'll get to see this at all. Doing too many things in one time. I don't think you got this diagram. Am I right? Yeah, Eugene. Do y'all have this diagram or no? Can you check? If no, tell me. I will upload again.
We do have that diagram.
Oh, you do have? Wonder how. We do have. I wonder how that happened. Because it's outside the page. I'm surprised it works. Okay. So this is this example. Thank you for letting me know. Okay. So this is an example of unsymmetrical loading. Okay. So the first thing we have to do now. So the formula, I'm going to write up the formula. Okay. So the formula where we're going to apply is stress X is equal to my over Iyy multiplied by Z plus by mz over Izz multiplied by y. Okay, I'm going to put the minus down here. Just follow the textbook in terms of formula. But don't worry about the plus or minus. Okay. So the first thing that we have to do, I'm going to make this bigger. Okay. The first thing we have to do is we are going to find our m. Right, our my, and then sorry, our mz, and then we're going to find our my. Okay, so the first thing, so this is our my, and then we're going to find our mz, and we'll be made aware that this angle over here is 20 degrees. Okay, we'll be made aware. So we are going to find our my is equal to m sine theta. Some of you will already know that this is really easy already, right? 10 times 10 to the power 3 multiplied by sine 20. Okay, so sine 20 times 10 to the power 3 is equal to 3.42. Okay, so 3.42 times 10 to the power 3. And then we're going to deal with our mz, m cos theta. So it's 10 times 10 to the power 3. Okay, cos 20. So 10 to the power 3 times I cos 20. Okay, so this 9.3. I'll call it 9.4. Okay. Then I'm going to use the magic arrow that we have created. Okay, so I'm going to use our magic arrow. Okay, so copy, paste. Okay, so the magic arrow will tell you what is tensile compression, and I'm going to use the other magic arrow. So no need to think, brainless, Okay. So we know that mz, right, based on mz, right, our moment vector is going this way, right? So we know that this is compression and this is tensile, and then on the other side we know that moment about y, this is compression and this is tensile. Okay, then the next confusing thing, right? So we know this, we know this. Okay, the next confusing thing is what is IYY and what is IZZ, right? But you no need to worry, okay? Because I hope I taught you well how to find your MYY and MZZ, okay? So I'm going to paste here, okay? So we are going to find, okay, so the first thing, I know the formula is really, really easy, okay? I understand. So we need to find what is your IYY. We're going to find IYY. So as I said, this is the problem, okay? Students know the formula, but what is I? So IYY is, I'm going to use the green, okay? So if this is my YY axis, right? This is our YY axis, right? So we know that parallel to it is our width, perpendicular is our depth, right? But the problem is IYY, where is the centroid, right? Where is the centroid about Z bar? On the Z axis, where's the centroid? I don't know. Okay, you cannot say it's exactly. You cannot say is exactly. You cannot say is you. We have to find whether is it here, here. I don't know. We don't know. Okay, so we have to find centroid. Okay, we have to find the centroid. So we have to find centroid Z bar. Okay, so I'm going to call this 1, and I'm going to call this 2. Okay, so we already know what is our width, okay, and what is our depth. Okay, so where about